eigenvalue equation of an operator is the equation of this type. Here lambda is an unknown scalar, phi is an unknown vector, and A is an operator under consideration. To solve the eigenvalue equation means to find all possible values of lambda for which it can hold, and for each such lambda to find the set of vectors which satisfy the equation with this lambda. All lambdas satisfying the equation are called the eigenvalues of the operator, while the vectors corresponding to those lambdas are called the eigenvectors of the operator. Let's look at some properties of eigenvalues and eigenvectors. First, if we have some eigenvector phi corresponding to some eigenvalue lambda 1, then for any complex number alpha, alpha phi will also be the eigenvector corresponding to this lambda 1. To eliminate this ambiguity, we can choose to normalize the vectors, which are the solutions of this equation. Now suppose that for some eigenvalue, let's call it lambda 2, there are p linearly independent eigenvectors. Then it is quite obvious that any vector constructed as a linear combination of these p eigenvectors is also the solution of the eigenvalue equation with lambda 2. This means that each eigenvalue defines the subspace of the initial space, and each vector of this subspace is an eigenvector corresponding to this value. Eigenvalue which has more than one eigenvector is called degenerate. The degree of degeneracy of an eigenvalue defines the dimensionality of the eigen subspace. The eigenvectors have the geometrical meaning of some special directions untouched in some sense by the operator. If the operator, for example, rotates the three-dimensional Euclidean space around some axis, then this axis itself would not be touched by such rotation. Thus, it is going to be an eigenvector of such operator with eigenvalue 1. Now, if this rotation is by angle pi, then the whole plane orthogonal to this axis preserves the direction of its vectors. They are just multiplied by -1 by this rotation. This plane is two-dimensional, which means that eigenvalue -1 is two-degenerate in this case. And this plane, orthogonal to the axis of rotation, is two-dimensional eigensubspace corresponding to this value. It is quite obvious that two different eigenvalues cannot have mutual eigenvectors. In an n-dimensional space, an operator can have at most only n linearly independent eigenvectors. Each such vector corresponds to some eigenvalue, and some of them can correspond to the same degenerate eigenvalue. This all means that the eigenvalue equation of an operator in an n-dimensional space can have at most n solutions, n eigenvalues. The eigenvalue equation is a powerful instrument for operator analysis in general. But from now on, we are going to concentrate on a very special case. We will consider only finite-dimensional spaces, which we deal with when we consider qubits, and we are going to examine only Hermitian operators. Now, for Hermitian operators, the solutions of this equation have additional properties. First, it is easy to show that eigenvalues of a Hermitian operator are always real. The complex or imaginary part is 0, always. Second, the eigenvectors of different eigenvalues are mutually orthogonal. This is a very important property. It means that for a Hermitian operator in a finite-dimensional space, we can construct an orthonormal basis of its eigenvectors. And even if some eigenvalues of the operator are degenerate, we still can do that, because in the eigensubspace of a degenerate eigenvalue, we can choose any eigenvectors we want. So we can choose orthonormal set of vectors there. So each Hermitian operator defines an orthonormal basis. And we remember that each orthonormal basis in the state space defines a set of possible values of the system measurement. So now we can give, at last, the strict mathematical definition of an observable of a quantum system with a finite-dimensional state space. And here it is. An observable is a Hermitian operator acting in the state space of the system. The eigenvectors of these operators are the measurement outcomes. They are the states to which the system can collapse after the measurement. And when it does, the classical outcome that we obtain as a result of the measurement is the eigenvalue, which corresponds to that eigenvector. This is all good, but wait. We know that some eigenvalues can be degenerate. So if the system collapses to some vector from the eigensubspace of a degenerate eigenvalue, we obtain only that eigenvalue, and we can tell which vector represents the system now. So we must admit that in this case, the system collapses not to a single vector, but to the whole eigensubspace. It is very true. So it is much better if we have an observable with all eigenvalues being non-degenerate. But if we don't have one, we can use a set of several commuting observables. It can be proved, and this is a fundamental theorem in quantum mechanics, that if two observables commute, one can construct an orthonormal basis of their common eigenvectors. So if we manage to implement a set of commuting observables, such as for each their common eigenvector corresponds a non-degenerate eigenvalue of one of them, we will be able to obtain the most possible information about the state of a quantum system using this set of observables. Such sets are called the CSCO, the complete set of commuting observables. However, we are not going to discuss these CSCOs further here, since most of the observables we are going to use have all non-degenerate eigenvalues, thus representing the complete set of commuting observables alone. I believe that it is time to observe some examples.